Part 3, reflection. Light travels in straight lines through a medium that is uniform. This characteristic is termed rectilinear propagation. The light falling on a flat, smooth, reflective surface, such as a mirror, undergoes specular or regular reflection. This is an example of regular reflection. The light rays come in and bounce off, and they're all nice, uniform, perfect. Okay, this is why the water of a lake on a nice calm day makes a perfect reflection. On a windy day, the water surface gets to be a little bumpy. This causes the light rays to bounce off at different angles, making a blurry reflection or no reflection at all. This is called diffuse or irregular reflection. And as you can see, as the light rays bounce, okay, they all bounce off at different angles. It's all weird, very bad. Okay, well, not bad, just bad if you want to see a reflection. So, the law of reflection, okay, particular terms are used to describe reflection. Reflection will occur when an incident light ray contacts a smooth reflecting surface. The incident ray makes contact at the point of incidence and then leaves the reflecting surface and becomes the reflected ray. If, at the point of incidence, an imaginary line, called the normal line, is drawn perpendicular to the surface, then the angle formed between the incident ray and the normal line is called the angle of incidence. The angle formed between the reflected ray and the normal line is called the angle of reflection. Okay, so let's just have a look at some of those things. Okay, so we have the incident ray. We're starting this way and we're going in. Okay, so at the point of incidence, that's where it hits the mirror, we draw this 90-degree line, okay, called the normal line. Okay, the angle of incidence is measured from the ray to the normal line. Awesome. Okay, so that's the angle of incidence, and then of course the angle of reflection is from that normal line to the reflected ray. Okay, that makes sense? Perfect. Okay, simply put, the law of reflection is the angle of incidence equals the angle of reflection, or angle I equals angle R, when the two angles are always measured from the normal line. Okay, so example 1, what is the angle of reflection for the light ray in the diagram below? Okay, so first things first, we draw in the normal line. Wow, that was bad. Okay, let's try that again. Okay, so there, that's a little better. So remember, the normal line is always at 90 degrees to the surface. So in this case, the angle of reflection, the angle of incidence would be 60 degrees. Now, that's because the normal line always intersects the medium at 90. So if that whole angle up there is 90, 90 minus 30 is 60. Awesome. Okay, and then of course the light ray bounces off like that. So this angle here, the angle of reflection, would also be 60 degrees. So what is the angle of reflection for the light ray? The angle of reflection, angle R, equals 60 degrees. Okay, easy enough. Example 2. A ray of light is reflected in series from two mirrors, A and B, as shown in the diagram. Okay, what is the angle of reflection from mirror B? Okay, so as you can see, so there's 40 degrees here. That's the angle of incidence. So the angle of reflection is also 40. That entire angle is 90 degrees, so that makes this little guy right in here, that makes that one 50 degrees. Okay, now remember, there are 180 degrees in a triangle. So that if this is 110 and 50, that makes 160. So there's 20 degrees left for that angle. Okay, well, of course, now we draw the normal line to here. Remember, the normal line intersects at 90 degrees, so that means that this angle has to be 70 degrees, which means the angle of reflection off of mirror B is 70 degrees. Angle R, and let's call it B, equals 70 degrees. Okay, angle RA, of course, that was the 40 degrees. Not that we need that, because it's specifically asking for this one, but that is how we label it if we actually had to. Okay, moving on. Image formation in a plane mirror. Okay, while image formation is not critical in plane mirrors, so flat mirrors, it is later with curved mirrors and lenses, so it's easier to understand here with the straight ones. Okay, if we look at the image of an object formed in a plane flat mirror to the side, okay, consider what the dashed lines represent. Okay, so the image looks like it's coming from here. Okay, now the dashed lines are extensions of the reflected rays that your brain interprets as coming from behind the mirror. This is why we perceive the image as behind the mirror. Okay, no big deal. So the light rays, okay, from the object, okay, they bounce out, bounce in, and our brain perceives these dotted lines as being behind the mirror, so it looks like the image is behind the mirror. Now, of course, the light rays actually come from the object, or the point object, okay, and our brain interprets the image as being behind. Okay, no big deal. Okay, we know the image can't be behind the mirror. The light rays only appear to be coming from an image, but that image is not real. The image formed in a plane mirror in this fashion is therefore called a virtual image. Okay, so we have those dotted lines. Okay, the image isn't really there. We know the image really isn't there. Okay, so it's called a virtual image. Here, I'm going to write in blue some more. Okay, for example, if you were to hold a piece of paper behind the mirror where the image appears to be, you would not see the image on the paper. But you wouldn't see the paper at all, right? Because you can't see through a mirror. Okay? By contrast, a real image is one that can be formed on a surface, such as a piece of paper. A projector is a familiar device that produces real images on a screen. Ray diagrams, like the one above, can be used to show how images form with a reflecting surface, such as a mirror. Okay, so image characteristics. When an object is placed in front of a mirror, the image formed can be described by 4 general characteristics. First, the magnification relates to the size of the image and the size of the object. The image can be enlarged, diminished, or the same size as the object. Okay, so magnification, bigger, smaller. The image attitude describes the image as being either erect or upright or inverted, upside down, relative to the object. This is termed vertical inversion. Horizontal or left-right inversion can also occur. We really don't talk about it in Physics 30, but you should at least know that it exists. Okay, the position describes where the image forms relative to the mirror surface. Okay, so either in front of the mirror, behind the mirror, that kind of thing. Okay, awesome. And of course, the type of image distinguishes between real and virtual images. A real image is one that can be projected onto a screen, and a virtual image is one that can only be seen or photographed. Right? That's why you can take a selfie. If you take a picture of yourself in the mirror, okay, it'll actually show up. So, okay, awesome. Okay, so there's 4 image characteristics. Okay, so let's talk about image formation in a curved mirror. Curved mirrors come in a variety of shapes, the most common being spherical. Okay, imagine a hollow sphere with a polished mirror surface inside and out. By removing a section of the sphere, you'll produce a double-sided spherical mirror with a concave reflecting surface on one side and a convex reflecting surface on the other. Okay, remember, convex is this side, okay, the side out. Concave is the inside, so kind of caved in. So the convex part is the outside, the concave part is the inside. Awesome. Okay, so a concave reflecting surface is curved inwards. Okay, so if we draw it this way, okay, so the little lines represent kind of the back side of the mirror. Okay, so that's what a concave mirror looks like. The surface is referred to as a converging mirror since it causes parallel light rays to converge or come together after being reflected. So the idea is if the reflecting light rays kind of bounce, okay, and they converge at a single point. We'll talk about that at length here in a minute. Okay, the convex reflecting surface is curved outwards. This surface is referred to as a diverging mirror since it causes parallel light rays to spread out or diverge after being reflected. Okay, so here's the surface of the mirror on this one. If we get parallel light rays, okay, so they now spread out as they reflect. Okay? As with plane mirror image formation, ray diagrams are useful to determine how images formed from curved surfaces. Ray diagrams for curved surfaces are more complicated, more complex, and involve an expanded set of terminology. So we need to learn some new words. Okay? So the first one is the center of curvature, C, the point in space that would represent the center of the sphere from which the mirror was cut. Okay, so let's put these on the picture as we draw them. In our picture down below, this point, little dash mark, that's the C. That is the center of, if we made this entire thing a circle. Okay? Awesome. So let's take those off. Okay, awesome. So that's C. Okay, 2, the radius of curvature. So that's labeled R. The distance from the center of curvature to the mirror surface. So this distance here, that would be labeled R. That makes sense. It's a radius, right? Awesome. V, the vertex. Okay, this is the geometric center of the curved mirror surface. So this is V right here. Okay, awesome. Okay, the principal axis, or the PA, is the imaginary line drawn through the vertex perpendicular to the surface of the curved mirror at this point. So this little line is the principal axis. Okay, great. Okay, the principal focal point, the point where light rays that are parallel to and close to the principal axis converge or appear to diverge from after being reflected. Okay, so the principal focal point occurs right here, halfway between C and V. So this is point F. Okay, awesome. Okay, and then the focal length, small f, is the distance from the vertex to the focal point, measured along the principal axis. The focal length is related to the radius of curvature by f equals r divided by 2. This means that the radius of curvature is reduced, as the radius of curvature is reduced, so too is the focal length of the reflecting surface. Okay, so this is where the focal point is, and this distance from F to V, that is called the focal length. Okay, so there's some words that we just need to know, and trust me, we'll get the hang of them. All right, drawing ray diagrams for curved mirrors. The 4 general image characteristics of magnification, attitude, position, and type can also be applied to curved mirrors. For curved mirrors, the normal line at the point of incidence is the same as the extension of the radius of the spherical surface drawn at this point. The law of reflection still describes how the rays will be reflected. To understand and predict how images are produced from curved mirrors, the features of the mirror and 2 of 3 special rays are used. These rays are drawn from a point on an object to the mirror and then reflected to locate the corresponding point on the image. The third ray can be then applied just as a verification. Okay, I'm going to encourage you guys to have a ruler when you're doing this. I won't have one because every time I put a ruler down on the screen it makes extra lines, so it's weird. Okay, so you use a ruler, and these are just for general ideas on how these things work. Okay, so we're going to draw an object as an arrow going up. Okay, so that's my object. So ray 1 travels from a point on the object parallel to the principal axis. Okay, so we're going to draw a line parallel. Oh, come on, line. There we go. Parallel to the principal axis. Okay, now any ray that is parallel to the principal axis will reflect through the focal point on a converging mirror or appear to have originated from the focal point on a diverging mirror. So if we put the object on the diverging one, okay, so we have, there we go, parallel to the principal axis. On the converging mirror, this thing, so this is the center, so here's the focal point halfway through. Okay, focal point halfway. Okay, so then any ray parallel to the principal axis will bounce through the focal point. On a diverging mirror, it bounces out as if coming from. See, this is the dotted line, and then the ray will bounce and look as though it's coming from the focal point. Okay, ray 2. Ray 2 travels from a point on the object towards the focal point. Okay, so we're going to go here. I should draw in red now. You know what? I'll draw in orange. Just shake it. Okay, so ray 2 goes through the focal point. Now, any ray that goes through the focal point bounces out parallel to the principal axis. Okay, now see where these two lines intersect? Boom, that is where the image forms. Awesome. Okay, on a diverging mirror, so this is going to go towards the focal point. Okay, so dot, 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 dot. Okay, so right there. Okay, so this then bounces out parallel. And what happens is we make a dotted line that goes straight. Okay, now, whoa, that was weird. Okay, so the blue dotted line and the straight orange dotted line, that's where the image gets formed. Wow, can barely see that. Sorry, my bad. It's this arrow right there. Okay, so you can see on a converging mirror, or diverging, sorry, the image is really, really small. Okay, now, ray 3 travels from a point on the object towards the center of curvature. Any ray passing through the center of curvature on a converging mirror or is directed back from the center of curvature on a diverging mirror will reflect directly back along that path. So if I draw in red now, okay, if I take this object, okay, and I go through the center of curvature, okay, that line will be drawn exactly back. Okay, so it goes one way, then gets reflected exactly backwards. Okay, now, that's the third ray. Okay, now, you can see that mine don't quite line up, and I know why here, because this orange line, I have drawn it. Okay, now this is why drawing with a mirror is really helpful. Mirror, drawing with a ruler. Okay, so I have to go through the focal point, actually hit the focal point this time, and then bounce straight. Oh, look, now all three lines line up. Okay, so that's where the image is. Okay, so you have an upside down little arrow where all three rays intersect. Okay, so you only need to draw two of the rays. Okay, the third one is just as a check. Okay, but those are the three rays. The one that goes parallel and bounces through the focal point, the one that goes through the focal point and then out parallel, and then the third ray, of course, goes right through the center. Okay, so clear as mud. I know. We'll work with these some more. Okay, I'll try and be more accurate. Okay. These three rays alone will allow you to predict and verify the location and characteristics of the image. Notice that some conventions are used when drawing these rays. Objects are often drawn as upright or erect arrows, so we just draw an object like that. Okay, real rays are drawn as solid lines. Okay, virtual rays, the ones that appear to exist behind the mirror, are drawn as dashed lines. Okay, so we'll use those here in a minute. For a converging mirror, so concave, there are 5 cases that must be considered. For a convex mirror, though, there's only one. These are explored with ray diagrams. Okay, so let's look at case number 1. Case 1, the object is placed at a distance outside the center of curvature. So remember, the center of curvature is that little dash, so we're going to put the object way over here. Okay? Now I'm going to draw as straight as I can. Remember, you guys should use a ruler. Okay, so if we draw the first line, okay, that goes straight out, okay, and then through the focal point. Now remember, that little dot is the center of curvature, so I should have put that tick on there for you. But, oh well, we can do that now. Okay, so, and then through the focal point. Awesome. Okay, then the second ray goes through the focal point. Through the focal point and then bounces straight out. Okay, and then we have our image right there. Okay, so we can see from this, okay, the light rays actually bounce there. Okay, we are on the correct side of the mirror. Okay, so this image is called real. If the image formed back here somewhere, that would be called virtual. Okay, it doesn't do that, so this is called a real image. Okay, you can tell the arrow is upside down, so this image is said to be inverted. Inverted, upside down, that's all good. Now, see where the lines or the rays crossed? We are closer to the mirror than the object. Okay, right? The object is this far away. The object is right from here to here. The image is only from there to there. So we can tell by that this image will be smaller. Here, we'll erase those lines. It gets messy if we don't. Okay, so this is real, inverted, and smaller. Okay, so the distance to the mirror is closer, so the object itself is smaller. So real, inverted, smaller, poof, done. Okay, awesome. Okay, so let's see what happens when the object is placed at the center of curvature. Okay, so the object, the line bounces out and down. Okay, the second one bounces through the focal point, okay, and straight out. If you have a look at that, that actually hits at exactly the same spot. So it's still on the correct side of the mirror, so it's still real. It's still inverted, but this time when you place it right at the center of curvature, the object is the image, is the same size. Okay, what happens when we place the object in between C and F? Okay, so that would be like right here. Okay, again, please use a ruler. Okay, so you go straight and through the focal point. Okay, and now we go through the focal point and out. Oh, well, would you look at that? So this time, we're still upside down, we're still real, right? We're on the correct side of the mirror. So it's real, inverted. Okay, and this time, the object is further away, the image is further away than the object, so this is bigger. Okay? Larger, bigger, pick a word. Smaller, another word for smaller, of course, is diminished. Okay, so that one works. Okay, so real, inverted, and bigger. So case 4, what if we place it right at the focal point? Now this is kind of when the third ray would really help. Okay, so here we go to the mirror through the focal length, through the focal point. Okay, I'm going to draw, I'm going to use red, draw the one through the center of curvature. Okay, now I'm also going to draw the one through the focal length. Okay, the point is, look at these two lines. Even on my really crude diagram, you can tell that these are parallel. Okay, now parallel means that they will never intersect. So look, if I draw another one, because remember the second one is supposed to go through the focal point. Now you're at the focal point. So if we draw through the focal point, look, that arrow won't touch the other three either. other two either. The idea here is that no image forms. If you place an object at the focal length of a mirror, no image forms. It's like a blind spot in the mirror. Okay? And then case 5, the last one, is inside the focal length. Okay? So now let's see what happens here. Okay, so we draw a line to the mirror. Okay, and then it bounces through the focal point. Again, the second one really isn't as good here because the focal point length is behind. Like, we can draw it there. What's better to do is draw to the center of curvature. Now, in this case, if you have a quick look, in the case 4, the lines were parallel. In this case, and I'll just kind of make it so that it's a little easier to see. See, they are diverging from each other. There's an angle there. Okay, now when your brain sees image or rays like this, what it does is it interprets, okay, these things going, because they will intersect behind the mirror. Okay, and where these two intersect, that is where the image forms. Oh, well, isn't that interesting? So if you've ever seen or used a makeup mirror, okay, that's a makeup mirror, and you can only see an image when your face is really, really close to it. Okay, now look, this kind of image, the image forms behind the mirror. The light rays don't actually go there. Your brain just perceives them as coming there. So this is called a virtual image. So this is virtual. Okay, it is bigger. Okay, and it is upright. Upright or erect. Okay, so it is the same direction. So it points up. Okay, just like the object does. Okay, it is taller than the object, and it is on the wrong side of the mirror. That's what makes it virtual. So virtual, bigger, upright. Okay, now I have a summary table for you here. Okay, so there's actually 6 in this table. Now these two are really case 1. So distant or outside the center of curvature. Okay, so if you're really, really far away, like a planet, or, you know, just kilometers away, taking a big picture across a field maybe. Okay, so the images are real, inverted, and smaller. Now really close to the focal length. Okay, if you're just outside the center of curvature, it's real, inverted, okay, smaller, but in between F and C. So really those two are pretty much the same thing. Okay, then you have at the center of curvature, real, inverted, and same size. Between the focal point and C, so real, inverted, and enlarged. Remember, at the focal point, we get no image forming, and then inside the focal point, it's virtual, erect, and enlarged. Okay, the image forms behind the mirror. Okay, so those are the cases for a concave mirror or converging mirror. Okay, so for a diverging mirror, all diverging mirrors produce images in the same way. As such, there's only one way to draw them. Okay, so if we put an object over here, okay, you know what, let's make it bigger just because it'll make it easier for me to draw. Now, it's important to note that these are the kind of mirrors that you see in the back of the drugstore, okay, or the passenger mirror on a car. Remember, it says how objects are closer than they appear? Well, this is why. Okay, so if you draw a ray towards the mirror, it will bounce off as if coming from, whoops. Wow, sorry guys. That's crazy. Yeah, I'm not sure what happened there. Sorry, give me a sec. Alright, good enough. Sorry, my bad. Remember, that's the center of curvature, so here is the focal length. So that is going to bounce off the mirror as if coming from the focal length. Okay, now the next one, it goes to the focal length. So the object, okay, so to the focal length, and then it flies off straight. Now remember, these dotted lines intersect at the focal length, so that's not really helpful. So these dots really don't need to be there. Okay, it's the one here that needs to be. So remember, these dotted lines go straight back from the one parallel with the principal axis. It's these is where they intersect. That's the important one. And then if we go to the center of curvature, that's the same thing. Okay, so center of curvature. Okay, and then this guy here bounces straight back. Okay. Anyways, so those are the three rays. They all intersect right there. And you can see the image forms behind the mirror. So it's virtual. Okay, it is smaller. Right, it's really tiny. Okay, so virtual, smaller, and it is upright. Okay, virtual, smaller, and upright, and all diverging mirrors have this. That's why there's that little sign there, objects are closer than they appear, because they look smaller, so you think that they're further away. Well, they're closer than they look, because the mirror is making them look smaller. Okay, so object position anywhere in front of the mirror, virtual, erect, and diminished or smaller. Okay, awesome. So those are the image characteristics from a curved mirror. Okay, if you're not getting it yet, just have a little bit of patience. We'll go through some examples. Hopefully they'll be a little more clear. Okay, have faith. Okay, equations for curved mirrors. The general rules for drawing ray diagrams of curved mirrors in combination with the law of reflection allows us to generate several equations for use with curved mirrors. These equations can be used to determine the exact characteristics of an image. Ray diagrams are helpful in determining general characteristics, so they should be sketched, and we're going to sketch them in all our examples, but the equations provide the accuracy necessary. Okay, the mirror equation is 1 over f equals 1 over do divided by 1 over di. This is on your formula sheet. Okay, do is the distance of the object from the mirror. Di then is the distance of the image from the mirror, and f is the distance of the focal point from the mirror, or just called the focal length. Okay, so not a big deal, it's all good. Okay, further analysis reveals ratios between the distances of the object and image and the height of the object and image. Sorry guys, it looks like I didn't erase that, so this isn't supposed to be here. Sorry, my bad. Okay, so hi over ho equals di over do. Okay, where ho is the height of the object above the principal axis, and hi is the height of the image above the principal axis. Okay, and notice I didn't put that's not on your formula sheet. We'll get there in a second. Okay, recall the ray diagrams for concave mirrors. Often the image was upside down or inverted. In mathematics, such a reflection is denoted by a negative. As such, there are rules about when negative signs are used with the mirror equations. Wow. Okay, so let's talk about these sign conventions. Okay. Alright, sign conventions for use with the mirror equation. As we have seen previously, there are real and virtual images, which can form either in front of or behind the curved mirror. When using the mirror equation, it is therefore necessary to follow a sign convention which can distinguish the type of image formed. Okay, so real objects and images have positive distances measured from the vertex. So these are in front of the mirror. Virtual objects and images have negative distances measured from the vertex. These are behind the mirror. Erect images and objects have positive heights. These are above the principal axis. Okay, inverted images and objects have negative heights. These are below the principal axis. Converging mirrors, okay, so concave mirrors have a real focal point, and the focal point or focal length is positive. These are in front of the mirror. Diverging mirrors have virtual principal focal points, and the focal length is negative. These are behind the mirror. Negative signs are included as a result of sign conventions above and are used with the mirror equation. The result is that the ratio equation, a negative, is used to make sure the above conventions give answers that match the ray diagrams. So magnification is HI over HO, okay, which equals negative DI over DO. This is the version that's on your formula sheet. So they add that negative in to make sure everything works. Okay, so I want you to use these pictures to help you with this. Okay, so here the height is positive. Okay, so usually this is HO, height of the object. Okay, and if the okay, so this is the positive for height. If we're down below the axis, below the principal axis, our heights are negative. Okay, so usually, or almost always, the object is placed upright because that's how objects work. And sometimes if the height is this way, okay, then HI would be positive. If it's the other way, okay, if it's down this way, HI would be negative. Okay, so above the principal axis, we're positive. Below the principal axis, our height is negative. Okay, now we always put the object in front of the mirror. So there we go. So DI, okay, if DI is on this side, it's positive. Okay, DO is always positive. Okay, so DO is always positive. Okay, so if DI is on the correct side or the same side as the object, DI is positive. If the image forms over here, DI would be negative. Okay, awesome. Now here the focal length, okay, the focal point is on the correct side of the mirror. The light rays actually go here. Okay, so this is F is positive. On the diverging mirror, see the focal point is on the other side of the object. Okay, so the focal length, the light never actually touches the focal point, so this is when the focal point is negative. Okay, so here DO is still positive. Now, if the image that's usually going to form in here, okay, so that would be DI being negative again. DI is negative, F is negative, DO is positive. In this case, HI, the height of the image, would be positive. Okay, the height of the object would be positive, right? Because remember, up here, H is positive. Down here, H is negative. Sorry, positive is supposed to be positive, and H is negative. Okay, so hopefully those pictures help a little bit. And again, we'll do some examples and hopefully it all makes sense. All right, so let's have a look. Examples. Number 1, an object is located 20.0 centimeters from a converging mirror that has a focal length of 15. Where will the image form relative to the mirror vertex? Okay? All right, so before we even do this, we're going to draw a little picture just so we can kind of see what's what and how it all works. So it is a converging mirror, so that's a concave mirror. So kind of like that. Okay, I'm going to draw the principal axis in. Okay, the focal length is 15. Okay, so that means the center of curvature is like 30, and the object is placed at 20. So it's placed like that. Okay, great. So we are technically in between center and focal. So if you remember the characteristics, this is, I think, case 3. It's going to be bigger. Okay, so it comes this way and then in, this way, and oh yeah, look, it is. Oh, sorry, I should draw that. Okay, so through the focal length and straight out. Okay, so then the image forms right there. Oh, okay, so it is bigger. So this thing is real. The image forms on the correct side of the mirror. This is real. This is upside down or inverted. Upside down and bigger. And we know it's bigger because it is further away from the object. Okay, further away from the mirror than the object is. Okay, but now let's prove it. Okay, so in order to figure this out, where will the image form? So that's really asking for di. So 1 over f equals 1 over do plus 1 over di. Okay, so f, the focal length on this thing, that's on the correct side of the mirror. The light rays actually go through it, so that's positive. So 1 over 15.0 centimeters. Okay, the object is always in front of the mirror, so that's positive 20.0 centimeters plus 1 over di. Now, the mathematics doesn't change just because these are fractions. Okay, I want to get the 1 over di all by itself. Okay, right, we want to isolate the variable term. Okay, now how we do that, we simply subtract 1/20th over to that side. So we go 1/15 minus 1/20th. Okay, so 1/15 minus 1/20th. Okay, and that is 0.01666 repeating, so to 3 sig days, 0.0167. Okay, equals 1 over di. Okay, remember we just switch those two things and we get di equals positive 60.0 centimeters. Okay, so positive 60 centimeters. Awesome. Okay, so where will the image form relative to the mirror vertex? The image forms at 60 centimeters away. And it's positive, so that means, now I've drawn my picture, obviously not very well, okay, but that's all right. So this image should be like way over here somewhere if we were drawing to scale. So anyways, 60 centimeters, so it's a lot further away. So this is real. Now, we still can't tell that it's upside down, okay, but we do know that it's bigger because it's further away. So now let's look at B. If the object is 5 centimeters high, determine the attitude, height, and magnification. Oh, okay, well, we already know that it's upside down. That's the attitude. But let's prove it. Okay, so this equation we affectionately call Heidi-Hodo. Heidi-Ho-Do. Heidi-Hodo. Anyways, okay, so if the object is 5 centimeters tall, that's HO. Okay, so we get 5.00 centimeters on the bottom. So I want HI. Okay, negative. Now, DI was 60, so 60.0 centimeters. Okay, and DO, that was 20 centimeters. Okay, and then of course we cross multiply and divide, and we get HI. When we actually work that thing out, HI is negative 15.0 centimeters. Okay, well that makes sense because it should be negative because we know that it's upside down, but we also know that it's bigger. The object is only 5 centimeters, well this one is 15 centimeters. So of course the negative just denotes that it was flipped over. Okay, so the image height is 15 centimeters upside down. Okay, awesome. And then, of course, magnification is either HI over HO or negative. See, we could have done the magnification first. Either or. It doesn't matter. We pick one. So the image height was negative 15.0 centimeters. The object height is 5.0 centimeters. So the magnification is negative 3. I guess 5.00. So you can say negative 3.00 times. Okay, so that of course is times bigger. Okay, and it's bigger because of course you're timesing by 3. And then of course the negative just means it's flipped over. So the magnification is negative 3.00 times. Okay, so hopefully that helps. Let's try the next one. Alright, number 2. A diverging mirror of focal length 10 centimeters produces an image of an object located 20 centimeters from the mirror. Okay, determine the image distance, and the magnification is the image real or virtual. Okay, so we have a diverging mirror. So that's this one. Okay, we are focal length of 10, so here's the focal length, that's 10, and we're placing the object 20 centimeters from, so about there. Okay, 20 centimeters-ish. Okay, close enough. Okay, determine the image distance, magnification, and is it real or virtual. So let's draw this. So remember, we go draw straight, and then out, and then straight to the focal point, okay, out, and, whoops. So then we draw the dotted lines. Oh, right. That's one of these. So this is behind the mirror, so this is virtual. So we've already answered that part before doing any of the math. Virtual, erect or upright, and smaller. So those are the characteristics. Okay, so that's nice. So we've already answered the second part. Okay, determine the image distance and the magnification. So image distance, remember that's di. So we go 1 over f equals 1 over do plus 1 over di. Okay, now what do you know about the focal length on these ones? The focal length, f, is behind the mirror. The light rays never actually touch it. Okay, so the focal length is negative. So this is 1 over negative 10.0 centimeters. Okay, DO is always in front of the mirror. You can never place an object behind the mirror. Okay, so that's 1 over 20.0 centimeters plus 1 over DI. Okay, so again, we just move that over. So 1 over negative 10 minus 1 over 20. Okay, and that just works out to a decimal. Okay, so that is negative 0.150. Okay, equals 1 over di. Okay, and then we just switch those two, so di equals, okay, negative 6.67 centimeters. Okay, well, all that means is that it's 6.67 centimeters behind the mirror. Okay, so that's this distance right there. The negative means behind the mirror, which we already knew, and the 6.67 is how far. Okay, awesome. So that's not too bad. Okay, so again, 6.67 centimeters behind the mirror. Okay, that's how we interpret that. Okay, and then magnification. Okay, we don't know the heights, but we don't need the heights because we can use the negative di over do. Okay, so negative, and then di is negative 6.67. See how the two negatives are going to cancel? Okay, and then do, we know, is positive 10.0 centimeters. Okay, so 6.67, oh, I said 10 centimeters, that's fine, that's focal length. Okay, the do is 20 centimeters, haha, funny. Okay, sorry about that. So 6.67 over 20. So here I have to write down here. I'm running out of room. Sorry, guys. Okay, so that is 0.333 times. Now that, of course, is also 1/3. Okay, so if you can recognize the fraction, feel free to put it. But if sometimes it's not a nice fraction, so just use the decimals. Okay, so 0.333 times. Now that should make sense because it's upright. The two negatives cancel, leaving you with a magnification. It's getting smaller, okay, but it's still upright, so the magnification should be positive, and of course it is. Okay, so the magnification is that one. Okay, so the image is 6.67 centimeters behind the mirror, and it's magnified by 1/3. Okay, great. Number 3. Determine the image distance, magnification, and attributes for these ones. Okay, so we have a converging mirror, focal length of 12, and the object is 6 from the mirror. Okay, all right, so we have a converging mirror again. Okay, the focal length is 12. Okay, and the object is placed 6 centimeters. So we're inside the focal length. Ooh, this is one of those crazy ones. Okay, so remember, we go straight out and then back to the focal length. Okay, and then if we draw right to the focal length, okay, see how these lines converge. Sorry, I've drawn it really poorly. Okay, we're going to take that off. Okay, there we go. Okay, these ones, it's easier to draw the center. Even with my crude diagram, it'll be a little better. Please remember to use rulers because it helps. Okay, so if we draw from the center of curvature out, oh look, see how these lines, these two are getting further apart. That means our brain interprets these as meeting somewhere behind the mirror. Oh, right, this is that makeup mirror one. Okay, so you're inside the focal point. Okay, your image is virtual. You are bigger and upright. Virtual, bigger, and upright. Okay, now let's prove it. Okay, converging. Okay, so 1 over f equals 1 over do plus 1 over di. Now look, if we do this right, di should be negative. Okay, so f should be positive. The focal point is on the correct side of the mirror. So 12.0 centimeters equals 1 over 6.00 centimeters. Oh, just 6.0 centimeters plus 1 over di. Okay, so 1 over 12 minus 1 over 6. We'll bring that over. Okay, and we get a nice decimal for that. So 1 over 12 minus 1 over 6. Okay, that is negative 0.083. Okay, equals 1 over di. Okay, again, switcheroo for those ones. So just switch these guys. So di equals 1 over negative 0.083. So that is negative 12 centimeters. Okay, well that means we are 12 centimeters behind the mirror. Well, that makes sense because we know we're behind the mirror. We know it's bigger. Okay, so that's cool. Okay, so negative 12 centimeters behind the mirror, or 12 centimeters behind the mirror. Okay, awesome. Okay, and so that's the image distance. Magnification, we already did the attribute, so we just need the magnification now. So magnification is negative di over do. So negative 12 centimeters divided by do is 6.0 centimeters. Oh, look, the two negatives make a positive. Okay, and 12 divided by 6 is 2.0 times. Okay, so the magnification is 2 times. Okay, so that's that one. Okay, B, a diverging mirror, focal length 5, with an object 10 centimeters from the mirror. So again, diverging mirror. Okay, focal length of 5, so that's this guy. And we are 10 centimeters in front. Oh, well, that's one of these ones again. Okay, so remember, with the diverging mirrors, they're always going to be smaller, virtual, okay, and upright. Right, and just to prove it, see, it goes like this and like that, so that's the dotted line here. Okay, we get the line to the focal length, bounces straight out, and go, okay, and the image forms right there. Okay, so smaller, virtual, upright, that's the same for all diverging mirrors. Now when we do the math for this, 1 over do plus 1 over di, remember the focal length is on the opposite side. The focal length is negative here. So this is 1 over negative 5.00 centimeters. And that's just because the focal length is on the wrong side of the mirror. Okay, so do, we said we put the object 10 centimeters away. Okay, plus 1 over di. Okay, so 1 over negative 5 minus 1 over positive 10. So 1 over negative 5 minus 1 over 10. Okay, that gives us on our, when we actually type that in, we get negative 0.333. Okay, so sorry guys, I want to do that one because I'm not sure if that's just 0.3 or negative, so that's okay. I'll just type it in again. So 1 over negative 5.00 minus 1 over 10.0. Oh no, see, that's just 1 over 0.3. Okay, and then of course to get the sig digs, so it's just 0, 0. Haha, funny. Okay, so that equals 1 over di. Glad I checked. Okay, and then of course we switcheroo, so di equals 1 over negative 0.3. Okay, so there's our 0.333. So that's negative 3.33, right? Because we have 3 sig digs. Okay, centimeters. Well, we already know what that means. It means it's behind the mirror. Well, it should be behind the mirror, absolutely. Okay, and then of course magnification. Okay, negative di over do. So negative 3.33 centimeters. There we go. Divided by do, that was 10.0 centimeters. So this one, that equals, the two negatives cancel, so 0.333 times, or of course 1/3. So the magnification is 0.333 times. Okay, and that makes sense because it is upright, so it should be positive. Okay, awesome. Oh, I know. I put a lot of examples in here because this is so confusing for kids. So like I say, I put lots of examples so that you can look at these again and just try and make heads or tails of it. Okay, so then C, a diverging mirror, focal length 10, object 2 centimeters from the mirror. Ooh, diverging again. Okay, so diverging, we're over here, focal length is 10. Okay, and the object is 2. Okay, well, it's diverging again. So this is going to be virtual, smaller, and upright. Because it's always those. If you're not sure, draw it. So it goes straight and then reflects out as if coming from the focal point. And then if you draw to the focal point, and then of course it bounces straight, okay, and the dotted line goes back straight as well. Oh yeah, look, there's the arrow. It's behind the mirror. It's definitely smaller, and it's pointing upright, so it's upright. Awesome. Okay, so we already have the characteristics. That's great for the pictures. Really important you learn to sketch those. And then 1 over f equals 1 over do plus 1 over di. Okay, so oh look, the focal length is behind the mirror, so it's negative. So 1 over negative 10 centimeters equals 1 over 2.0 centimeters plus 1 over di. Okay, so 1 over 10 minus 1 over 2, right? That guy comes across, it becomes negative. Okay, so that is negative 0.60 equals 1 over di. So then di equals negative 1.7 centimeters. Okay, so that's that, 1.7. Okay. Okay, so of course that means 1.7 centimeters behind the mirror, and magnification negative di over do, so negative 1.7 centimeters divided by do was 2.0 centimeters. Okay, so that works out to 0.83 times. Now, if you make that into a fraction, that's actually 5/6. I don't expect you to know that, okay? But if sometimes your calculator will put it into a fraction for you, that's fine. So 0.833333 times, okay, 5/6 times bigger. So you can tell that it's smaller, but it's positive, which means the image is pointing upwards. Okay, great. Look at us go. Okay, a few more, and then I will let you guys get to work. Crazy. Okay, number 4. 5 centimeter high object is placed 2.0 centimeters in front of a converging mirror. Okay, so that's this one. Okay, and is magnified by -4. Where does the image form, and what is the focal length of the mirror? Okay, so we're in here. Okay, so 5 centimeters tall, so it's a converging mirror. Our object is 5 centimeters tall. Okay, it's placed 2 centimeters in front of a converging mirror, and the image is magnified by -4. Oh, okay, well, tell you what. Magnification is HI over HO. So if I know that my magnification is -4, and I know that my image height is 5.0, sorry, my object height, my HO, okay, so that means my image height is going to be -20.0 centimeters. Okay, so that means it's upside down, and it's 20 centimeters tall. Well, remember, if you are inside the focal point, you get an image taller, but it's upright. So that would have a magnification of +4. The only way to do this to -4 is have the object form down there. Now, in order to do that, we have to be outside the focal point. Remember, it's going to go like this, and then like that, and then like that, and then like that. Okay, so that's the idea. So we are outside the focal point. The object is, the light rays are actually going to go there. So this is a real object. It is real, it is bigger, and it is inverted. So we know the characteristics right off the bat. Okay, now, where does the image form? So because it's real, it forms in front of the mirror. The image forms in front of the mirror. Okay, awesome. And then, of course, what's the focal length? So we go 1 over F equals 1 over DO plus 1 over DI. Okay, we want the focal length. Uh-oh. Wait a second. Object is placed 2 centimeters in front. So that's the DO. Ooh, I've got 2 variables there, though. Oh, right. Because we know that magnification is also equal to -DI over DO, right? So the thing is, our magnification we know is -4, okay, and there's no sig digs on that. It's when they say -4, that means exactly -4. Okay, so we're good. So -DI and then DO we know is 2 centimeters, 2.0 centimeters. Oh, look, there's 2 negatives. Those are going to cancel. Okay, and then DI is just going to be 8.0 centimeters. Whew. Okay, that's good, because now we have all the stuff for our formula, right? When we do that, we multiply the 2.0 up. So -4 times -2 is -8, but -8 would be -DI, so the 2 negatives would cancel. So DI is 8. So 1 over F equals 1 over 2.0 centimeters plus 1 over 8.0 centimeters. So that's decimal there. 2.0 and 8.0. So when we figure that out, that is 1 over F equals 0.63. Okay, and that makes F to be 1.6 centimeters, right? We just switch those two. Okay, notice that F is positive. It should be in converging mirrors like this. Okay, we know that DI is 8. Yeah, it's further out than the object. That's why it's bigger. Okay, so all of our numbers make sense with our attributes that we figured out earlier. So it's real, bigger, inverted, and the focal length is 1.6. Awesome. All right, we are almost there. Sorry. Flipped the page and shouldn't have. All right, 5. A 4.0 centimeter high object is placed 15 centimeters from a concave mirror, focal length 5. Okay, determine the image characteristics using a ray diagram and the mirror equation. Okay, so when it wants stuff like this, okay, we know that it's a concave mirror. Okay, so when it just says determine the characteristics, okay, we do that just like normal. The focal length was 5. Okay, it's placed 15, so it's a way out here. Okay, so we're going to go like this and like that. Okay. So the characteristics, we know that this is real. We know it is upside down. And we know that it is smaller. Now, if we look at our formulas, because it just says determine the image characteristics, so that means we have to solve everything. Okay, so if we look at our formulas, so 1 over f equals 1 over do plus 1 over di. Okay, I know f and I know do, so this, because I want the characteristics, I have to find di. And we go Heidi Hodo. Okay, I know the HO. I'm going to know the DI and the DO, so I have to figure out the image height. So I have to figure out the HI, and I will also have to figure out the magnification on this. So that is just the wording of the question, so you will have to do that too. Okay, so the focal length on this is going to be positive. Okay, because, right, the focal length on a converging mirror, it's on the correct side of the mirror, so it's positive 5.0. Okay, 1 over do, this thing is 15.0 centimeters, plus 1 over di. Okay, so 1 over 5 minus 1 over 15. So that gives us 0.13 equals 1 over di. Whoops. So then di equals, so we switch those, so 1 over 0.13, so that works out to 7.5 centimeters. Okay, so now we figure out hi, so hi equals negative 7.5 centimeters. Okay, the do we know was 15.0 centimeters. Okay, and the ho we know is 4.0 centimeters. Okay, so we cross multiply and divide for that, and we get h equals negative 2.0 centimeters. And we knew it was smaller, right? The original was 4 centimeters tall. The new one is 2 centimeters tall. So it is definitely smaller. And that negative, we infer that to be upside down. Awesome. And then magnification, of course. So hi over ho. So negative 2.0 centimeters over 4.0 centimeters. So the magnification is negative 2.0. Ooh, haha, funny, I went the wrong way. Okay, so negative 0.50 times, or 1/2. Negative 1/2. Okay, does that make sense? Well, I sure hope so. Okay, so magnification negative 0.5. Again, the wording of the question means we have to solve for everything. Okay, last one, and then I will stop talking for this video. I know this has been a long one. Thank you for your patience. You guys are awesome. Okay, so the reason I included this example is because they had one of these on the diploma exam a while back, and a lot of kids didn't really know what to do. Remember in the notes earlier, we had that table with the six possibilities for a concave mirror. Remember, there was only 5 pictures, but that 1 and 2 were the same, the distant. This is that one. So, okay, so light from a distant planet is incident on a converging mirror. The image of this planet forms on a screen 45 centimeters from the vertex of the mirror. Find the focal length of the mirror and the image characteristics. Okay, so we have a converging mirror. Okay, So the thing is, the converging mirror, and it's a planet, so the planet's like way out here, like really, 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 really far away. Okay, anyway, don't worry too much about that. So just put it out there somewhere. Okay, focal length is going to be here. It's going to be here. Okay, so it's going to be upside down, smaller, real. So real, upside down, and smaller. Okay, so we know the image characteristics before we do anything else. Okay, but the mathematics of this really confused a lot of kids. So, like I say, I wanted to include this just because of that. So 1 over f equals 1 over do plus 1 over di. Okay, so we don't know the focal length, and we don't know the do either. Okay, but we do know the di. The di is 45. Now, here's what I need you guys to consider, and remember, there's just an extra layer of think here. Okay, a distant planet. That's like really, really far away. So do is huge, absolutely huge. And 1 divided by a really, 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 really big number is just about 0. Okay, so this part here, mathematically, equates to 0. Like, it's so small, it's not going to affect the 1 over di. So 1 over f is equal to 1 over, well, di we know is 45.0 centimeters. Well, of course, if do is just 0, or something that's so incredibly small it's not going to affect that, then, oh, look, if we cross multiply and divide, or, again, just think, okay, f is 45.0 centimeters. That's it. Okay, so the image is, like, this image forms at the focal length. Okay, and that works for all things that are crazy distant. And you know what? It doesn't have to be hugely distant for that 1 over do to equal 0. So across a 200-300 meter field, like that's far enough. Okay, to make that 1 over do insignificant or just 0. So anyways, that's the idea. So the focal length of the mirror is 45.0 centimeters. And it forms a real, upside down, and smaller object, or image, pardon me. And it's a good thing it's smaller, because if it was a planet, right, like, planets are typically huge, so it kind of has to be smaller. But anyways, I digress. So that is that part. Okay, I want you guys to practice these this stuff, page 665, numbers 4, 5, 7, 8, 9A and B, and 10A and C, please. Okay, some good questions. Again, you can use right from your textbook or from the workspace card. It's completely up to you. Thank you for your patience. I know this was a long one. See you next lesson.